The talk is about the soil and the water relationships between soil and water. Because the water retention is a very important hydraulic property, not only for soil but for the whole ecosystem. It affects soil management and vice versa. It depends on soil characteristics and also it depends on soil on climate. That's it. Just a few words to remind you the concept of the texture, that is the particle size in the soil, clay, silt and sand. The structure, that is the way as these particles are arranged in soil. We know that in normal conditions, from the volume perspective, we have more or less 50% of solid particles and more or less 50% of nothing, of porosity. And something, 5%, 3, 4, 5, 6% of soil organic matter. This nothing is porosity and can be full of water or air depending on climate, irrigation, etc. From the weight composition, things are different. Most of the soil, 85%, is solid particles, more or less 12% is water, and 3% is organic matter. With regard to the soil structure, when these particles with the soil organic matter start the aggregation, you are forming voids and pores and aggregates of different sizes. So you have different ways of structures, having more or less bulk density depending on the pore size. We can measure the soil structure, the visu, looking at the shape of these different structures, but we can also measure some soil properties such as soil density, very related to soil porosity, the pore size distribution, the liquid retention, and the transmission and infiltration. All these properties are governed by soil structure. I'm going to mention, probably all of you know this, but I think it may be necessary. The bulk density is the mass of the soil divided by the volume of the soil. So the bulk density is including the porosity. Usually the ranges are from 1.1 to 1.6 grams per cubic centimeter. The particle density is the mass of the solid particles divided by the volume of the solid particles. So we are excluding the porosity. This is a value usually between 2.6 and 2.7 grams per cubic centimeter. And this is a very constant value. Of course, the porosity is the volume of pores divided by the volume of soil. In other words, you can calculate the porosity considering this formula. This is the bulk density, and this is the particle density. And then, if you have bulk density, you can have total porosity using this formula. The values of porosity are between 30 to 60% normally. Well, you know that when this porosity is completely full of water, you have a soil saturated, and the soil can lose the water by gravity. In that case, you will achieve this state called fill capacity or upper storage limit, which depends in the different characteristics of soil, is the maximum amount of water that a particular soil can retain. the soil can continue drying up to this wilting point, that is the amount or the volume of water that is in the soil, but it is not available for plants because it is very, very strongly linked to the soil particles and organic matter. The difference between the water and field capacity and the water in wilting point is the available water for plants. You have here this drawing, the soil, the aggregates. Between the aggregates we have these pores, and there is an important concept that the pore is not simply a void in a solid phase, because it produces some consequences. You can see that when this soil is drying, the smallest pores are conserving water. If we try to draw this relationship, we see that this is the height of water that can be similar to the head pressure, is maximum for the size, the small pore size, and is minimum for the big pore size. We can divide the pores between macropores, mesopores, and micropores. The difference between them, in a few words, is that macropores, of course, they are very big, they don't have the ability of capillary forces. They are filled with air at field capacity because they have lost the water. They may be caused by cracking, by the activity of animals, bad roots, etc. They are big pores. The function is aeration and infiltration. We can consider the size of micropores more than 75 micrometers. The mesopores are those filled with water at field capacity. And they are the pores for the storage of water and a slow movement of water inside the soil. They are very important for agriculture and irrigation because this is the water that the plants are going to have. This is the place where they are going to look for the water, the mesopores. They can be the size between 30 and 75 micrometers. The micropores, in turn, are filled with water at permanent wilting point, but this water is not for plants, it's for soils. They are very absorbed to the clay particles or to the soil organic matter, and they are important for the activity of microbes and also for chemical activities, for the redox reactions in this local, very small scale of the soil. We can say that these micropores are less than 30 micrometers. But the question of the size of pores is completely confusing. You can find a lot of different classification in the literature. In my opinion, you should choose one and be with this classification until the end of your research life. You can see all these different, they have different meanings, they have different advantages or drawbacks. You have to choose which is the best for you. From the pore size to the matrix potential. When you have this system with water, and this capillary force is producing that the water is going through the capillary, you are having something called a tension force, which drawing, is pushing or pulling. You understand me? No? The water is going up, and the component, the vertical component of this force is this one. Here you have this shape with a very small tensions, and this is the length of this capillary in the tube, in the pore. Therefore, the force that is here is T to PR cosine of half. And this force is able to retain the water that is in this capillary. So, there is the mass by the gravity. And the mass and the gravity is, what is this? Again, the area and the height and the density of water and the gravity. So this equilibrium is considering these two parts of forces. When you rearrange all these parameters, you have that the head pressure, that is the length of this H, the metric potential of the soil, is related to the tension of water, but is completely opposite to the radius of this capillary. The smaller the radius of the capillary, or the smaller pore space, the greater the pressure head potential, that is the metric potential. This is exactly the same as this. If we have different pore radius increasing from the left to the right, here we have the metric suction, H, and here we have the capillary height, which are related. H and T are completely related. So you are decreasing these forces when the pore size is increasing. On the contrary, when the soil is drying, you have more and more tension because the pores that are filled with water are very small. This is the basis of the water retention force. How can I measure the metric potential or the head pressure? We have a lot of different units, because pressure is a very important physical property in life, for everything. Maybe the most important are atmospheres and pascals, megapascals, kilopascals. But the bars, which are not in the international system of units, is everywhere. When you buy any device, these clocks are, most of them in bars, millibars, centibars. So we are living with the bars. We have to know what it is. There is a very interesting way to remember the equivalence between these units. Look, if you have 1 square centimeter and you need, I'm going to put 1 kilo here. How long must be this column to have 1 kilo here? How many centimeters? Is there? Yes, it's there. Yes, it's 1,000 centimeters long, and in this way you will have 1,000 cubic centimeters. This is
1 cubic decimeter.
1 cubic decimeter, and because it's water, 1 kilo. If we use the logarithm of this is the centimeters of water. Logarithm of centimeters of water is PF. This is, I think, and also centimeters of water are hectopascals. If you know these relationships, you are able to use any different table or figure, because sometimes you find curves with many different units. And regarding the states of water in the soil, different units with the same meaning. We were talking about the saturation of water. In this case, we have more or less 10 centimeters of water, which is not pressure. 10 centimeters of water is not a lot of weight. Or 0.1 pf, or 1 divided by 100 atmospheres, or 0 megapascals. In the field capacity, we have 2.45 pf, or 1/3 atmospheres, or minus 0.03 megapascals. In the water at wilting point status, you have 4.2 pf, 15 atmospheres, or minus 1.52 megapascals. And we can continue drying the soil. Dry at room temperature, we use this condition of soil dry many times, and this is equivalent to 5 pf. It depends, of course, on the weather, on the humidity of the air, etc. And we can continue drying the soil if you put this in an oven, 105 degrees Celsius for 24 hours, and then you are at 7 pf. This is the process, and these are the matrix potential in different soils, more and more dry. So, from the volumetric point of view, 50% solid particles, 50% pore size. If all the porosity is full of water, this is saturation. At field capacity, you are losing soil by gravity. Between field capacity and permanent wilting point, you have available water for plants, and this is hygroscopic water that is in the soil, but it is not available for plants. What is the relationship between porosity and texture? It's a bit tricky picture, but which one do you think it is which having more porosity? It's clay, yes. It's clay. Apparently, this is the sandy soil because it has a lot of big pores, but in reality, this is the sum of very, very much pore size. Therefore, the clay soils have more porosity, total porosity, than the sandy soils. And we can see this here again, just to remember you. This you already know, most of you, I think. clay less than 2 micrometers, silt from 2 to 50 micrometers, and sand from 50 micrometers to 2 meters. So, considering porosity and wilting point and field capacity, we have sand, loam, and clay. Particles are decreasing in size in this direction, but porosity is increasing. Field capacity is also increasing, but permanent wilting point is also increasing. Therefore, which are the soils having more water available for plants? Look at them.
The blue.
The blue? Who's the blue?
Reservoirs. Not clay.
No.
Not clay. It's the same zone. Which is
Low.
Yes, low. Please explain why.
Because the sand has bigger pores, there's more drainage, more water goes is running off, and the clay has too much matrix potential. So it adheres to water too much. So it's less available for the plant.
That's it. You are having the clay may have more water, but no more water available for plants because it has a lot of field capacity but a lot of wilting point. So the water available for plants is this. The biggest one is more or less here. I think that I have other. Here you can see better here. Do you like it? You have again the textures of soil, the field capacity, the wilting point, water unavailable because it is the matrix potential here is very high. So this is the loamy soil has the more water available for plants. In another figure, you can see that in this case, for example, the sandy, as you said, the sandy has a lot of gravity water, losing water a lot. Loamy, less gravity water, and the clay, very few losses of water. But if we look for the available water, you have 10 in sandy, 22 in loamy soils, and 12 in clay soils. What about the water available for plants and the soil organic matter? For a particular texture, for example, a loamy soil, you have this loamy soil texture with 1, 2, 3, 4, 5, or 6% of soil organic matter. When the soil organic matter increases, the wilting point increases. But what really is, where the increase is more patent is the field capacity. Therefore, if we put these two graphs together, we see that the fine particles do not increase the availability of water, but the increase of organic matter increases the availability of water. This is why it is very important to provide organic matter to the soils. If we have this graph, moisture here, volumetric soil moisture, and the matrix potential here, the modulus, the matrix potential is also negative, always negative. Which one is the clay, the sand, the medium clay, or the peat? A volunteer. For example, This
Sand.
sandy soil. Why do you think it is sandy soil? Why?
Because can't maintain easily water, so the plant would have to decrease the water potential to absorb, to take the water from the soil.
Yes, two things tell you that this is the sand. The vertical shape of this curve and the total porosity. The total porosity is the point when the curve touches this axis, where the matrix potential is 0. So this is the sand. What is the clay loam?
What's the difference between a clay loam and a medium clay? I don't know this classification.
Yes, I don't know, because this is a picture that I had from the internet, but I think that I don't use this classification either. I think that medium clay could be more finer than
30%
low.
clay is medium.
If we see, sorry. Yeah, well, this is this one. Clay loam has particles,
Some sand particles.
more sandy particles, and this one maybe more silt particles. And this is the pit, which is the total porosity of this pit. The total porosity.
90%.
Could be 90%. 90%. This is almost a sponge. This is the difference. We are looking this top about texture and the water available, the organic matter and the water available, and what about the structure and the water available for plants? It is very difficult to estimate the structure, to measure the structure. We can estimate, for example, the size of pores. And this can do thanks to the matrix potential. How do we measure the matrix potential? Is anyone here? Does anyone use this?
Me.
You. Could you please explain us how it works?
It's
Here.
really
A little something.
Okay, it is like a ball that you put the pressure inside, you can control the pressure, and in function that the pressure that you put inside the ball is, I don't know how to say in English, it's referring to one type of porosity or other. So you can measure different pF in function that you pressure that you put, so you can do the curve that she has described.
Mm-hmm. You have different pots. They are like the pots in the kitchen, very similar, but very reliable, because the pressure that you are putting here is dangerous. And you have a pressure pump here, and you introduce the pressure in the pot. Inside the pot you have samples. These samples are here. They can be disturbed or undisturbed. For example, these look to be undisturbed. When you are trying to measure the moisture, the high level of moisture of soil, you should use undisturbed soils. But if you are trying to measure soil dries, you can use disturbed soils. Do you understand what is disturbed and undisturbed? This sample, this is a cylinder that we took in the field, just burying it and excavating, and you have all the porosity here is as it was in the field. But if you take a sample and you put it in a bag and you carry it to the lab,
It is same as we have done in the last day taking.
yes,
That's good.
they are disturbed, and then you rearrange, you put these samples in a cylinder and you work with it, but the structure is lost. This is the difference. You saturate your soils and you put pressure inside, and then the water abandons your sample, and this water is collected. Then you close again the pumps and you calibrate or balance the pressures. You open the pot, you weight the sample, so you have one pressure, one weight. You do the process again, a second pressure, a second weight. It's a little bit long process. How much time does it take for you?
It's depending on the quantity of organic matter that the sample has, but it's to do all the PF, all the care, maybe 3 weeks.
3 weeks.
Yeah, for one sample.
For one sample or for several?
No, for one sample, because I'm using organic amendments, so it's to establish the weight of the sample. I need too much time.
Yeah.
I have a technical question. If you take this soil course, you normally should take it at mostly saturated situation, because if you bring them to the lab and water them there, they will I don't know how to say it, getting up, they're getting a bit bigger when they absorb the water, and then you would have to chop them. How do you deal with this in dry areas?
I'm going to explain this. I don't know why, because I have picture about that. The best way to sample these cylinders is first you have to saturate the soil. And we have your soil saturated that you break the sample.
You need a lot of water then in the field.
Yes. So, you have this kind of graphs here. You have different pHs selected by you and different weight of the sample. And you can transform the gravimetric moisture, that is the weight of water, into the volumetric soil moisture using the bone density. And then you have this graph, the volumetric soil moisture and the pF here. And you see how, when the soil is drying, the matrix potential is increasing. This is, again, the same water retention curve. The most useful thing that you can do with this is to notice where is the permanent wilting point, in this case in kilopascals. So you have 10% of water, the field capacity, 10 kilopascals, is more or less 28% of water, and in this case the water available for plants would be 28 minus 10. This is another way to measure this same water retention. I have the apparatus here. You can it's a little bit dirty because you see that the interiors of these apparatuses, basically you have two tensiometers with two different heights, and at the top of these tensiometers you have a cup with a certain porosity, you can see there, and this porosity has been measured in the laboratories or in the place where it is performed. We have here a reservoir of water, and we also have the pressure transducers here to measure what is the pressure in the system. What we do is to saturate the soil, and when the soil is completely saturated, we put it in a system. In the way that these two tensiometers are completely in contact, in a very good contact with the soil. As you know, when the time passes, you have the soil is drying. This is the image that you have to have in mind. You have two tensiometers, this is the porosity, and here are the transducers. The soil is getting dry, first here. There, the first tensiometer that is going to be dry is this one, and then we are going to have this one. This apparatus measures the different potential between these two curves, between these two porosities. The tension is increasing a little bit, increases. This is the stage 1. When the soil is drying, the matrix potential is increasing. You know already this concept. But then there is an equilibrium because this soil is drying and it knows that there is water here. And it wants this water. So there is a phase here when there is a fight for the water between the soil and the cup. Finally, the soil is the winner because it is able to broke this flow of water, and then the air enters in the tensiometer. When the air enters in the tensiometer, the tension drops completely. This is the air entry stage. Of course, we know that the pressure at the air entry is not 80 to 100 kilopascals. We know, because this is the material of the porosity, that it is higher. It is around 800 to 870 kilopascals. So, what is the innovation of this apparatus? Is that because they know that the air entry has been produced here, they extrapolate the curve with the air entry, and they say that this, in fact, this is the pressure at that moment. The two tensiometers, you know, this is one tensiometer is here in black, and the other tensiometer is here in gray, and this is the second stage, and therefore we are going to continue this stage, and suddenly it drops. This is the upper tensiometer, and you extrapolate and you say that this is 800 kilopascals. The second one continues a little bit until it drops, and this is the second one. With all these pairs of data, what you have is, this is the display of the program of this apparatus, and you are doing all these things you are doing with a sample on a balance. So you are measuring at the same time the pressure here and the weight that is losing day after day because it is drying. So you have gravimetric moisture, and you also have the matrix potential. And this is the result. You have this curve here. You can measure this because it is in the range of the tensiometer, but the rest of the curve is estimated thanks to this extrapolation. So you can have the complete retention curve from saturation to permanent wilting point. That is 4.0. I'm going to show you an example of some samples that we collected in the past here in the place that we are going to visit tomorrow, with different crops between the trees. These are olive trees. And for example, we have a treatment with tillage and treatments with vegetation cover. We take the samples, as you mentioned. First, you put the water in this big cylinder several times to perform or to study the infiltration with this single ring infiltrometer, and when you finish, you use this place to put this cylinder, and you can put it like this with one finger.
This is when you have only topsoil samples, right?
Sorry?
And then you have only topsoil.
Only topsoil. This is the Reservoir. Yeah. But you can excavate and you can have whatever you want. In this trial, we measure different things: infiltration, soil organic matter, bulk density, water retention, and hydraulic conductivity. Let me show you some results. This was the soil that was with reduced tillage compared with a soil with a cover, a permanent cover. The bulk density measured with a core sampling was more or less 1.37 for the tillage and a little bit smaller for the cover, but there were no significant differences. When we measured these samples, other samples in the high crop apparatus, we have the porosity of the cover was higher than the porosity of the tillage, with a quite good correlation between them. So apparently, the cover crops are increasing the porosity of soil, which is normal because the roots are creating a lot of voids in the soil. This is again the treatment with tillage and the treatment with cover, but in this area of the water retention that is not retained at all, from total saturation to the field capacity, so this is the gravity water. And in this case, we notice that the soil with tillage was a little bit, had a little less volume than the soil with the covers. Maybe this can be due to the organic matter produced by the crops. In the range of the soils with the water retained between 2.5 to 4.2 pF, there is a difference between the volumetric soil moisture in the covers that were higher, significantly higher than the soil tillage. This is very interesting because the farmers do tillage or make tillage in order to increase the water, when the reality is completely the contrary. They are having less water when they do tillage. And this is the hydraulic conductivity. With this high crop, you can also estimate the hydraulic conductivity, but this is for another war. Now I'm going to concentrate and to focus on the water retention. There are no differences in any case, but it seems that in the cover crops, the water moves more slowly, which is interesting because we want, in all this situation, what we want is to have a lot of water, but to maintain this water in the soil, we don't need a lot of percolation. Just a bit, of course, but not too much. We have to continue, we have to work a little bit more in this. What about the organic matter? Here, this is really the difference. The tillage has 1.3% of organic matter, and the soils here in the permanent cover crops has almost 2.1 soil organic matter. And this is compared to this graph that we saw before, we found these differences, and we see that probably the organic matter has more effect in the part of the humid soil that is in the field capacity than in the permanent wilting point. These are the results made with this apparatus. The retention course in the cover crops and the retention course in the tillage. I'm going to show you the average. This is the profile of the soil. This is the plowing horizon, 20 centimeters deep, no more. And we have here the pF and the volumetric soil moisture. This is the shape of the soil with tillage. More or less 46% of total porosity and 20% of water at the permanent wilting point. And this is the curve of water retention for the cover crops. It is not very spectacular, but this is the beginning. You have to think that this is only 3 or 4 years of experiments. We should need maybe 10 years to, or 20, I don't know, to obtain best differences. But what's the matter here? This is a gypsiferous soils that you are going to see tomorrow. And you know that this area is particularly prone to erosive processes, so this soil can disappear. And the new plants have to live here in this place. Do you want to see what is the retention curve of this soil? Yeah. This is. So, it's a big problem when, because of our land management, we are losing the soil in the first centimeters. We are going to deal with this kind of material, but it's not really soil. This is a geologic material. Probably plants would not be able to live there. And this is what, again, you are going to see tomorrow. This is the difference between the water at field capacity and permanent wilting point in these 3 soils. And the water available for plants in the tillage treatment is 10%, is 13% in the covered, and 8% in this horizon C1. Conclusion: the agricultural soil management can cause problems due to the compaction, decrease of soil organic matter, and with their effects on water retention. The cover crops, because they maintain greater residue, they are covering the soil, they are more fresh, they are less evapotranspiration in certain parts of the year. They increase infiltration and reduce runoff, they reduce evaporation from soil, and they increase soil organic matter. So this is a sustainable land management that should be used. You are going to laugh. Yes, because measure the water retention like this or with richer clays is very, very time consuming and as long as expensive. Look at this. This costs 2,050 or 3,000 euros, and this costs 25,000 to 30,000 euros. So, first, it is expensive, and second, it's time consuming. And probably, as I said here, if you are working in a very large area, it's impractical because you have maybe 100 or 200 or 500 samples, and you have to do this. You would need 10 years to have all of your data, or a lot of money and a lot of laboratories working for you, which is not practical. It's not impossible. So, the better transfers function have been developed to estimate the hydraulic functions of soil through more easily measurable soil properties. They use the parameters of Van Genuchten model and some specific soil properties, as I said. How does it work? It's easy. You can use statistical regression techniques, and you can use data mining and exploration, as you like very much. But you need a big databases with a lot of soils in order to have many data to compare and to obtain this kind of regression. You have dependent variables, in this case the moisture of the soil, and some coefficients related to some explanatory variables that are being using to explain the behavior of your soil. I can show you, for example, you have these papers uploaded in the Dropbox. In this example, 20 institutions from 12 European countries have been working together. These are the countries, and the number of samples that they provided to the database. And they had 95 soil units, up to 2,000 soil profiles, more than 5,000 soil samples, etc. With this, they put together 197,000 pairs of data of moisture and head pressure or matter potential. And with that, they created these regression formulas to know which are important and what variables you can forget. They also used, this is the Van Genuchten model, for a very well-known Van Genuchten model, to estimate the effective saturation from the moisture, the residual moisture, the saturated moisture, and a particular moisture that is related again with alpha, that is a parameter very important is related with the way as the water moves in the soil. It depends on the shape of the porosity and in the angles of these drops moving in the soil. Here it is related to the importance of the gravity for water to abandon the soil. And again, the head pressure and N and M, which are also parameters to help us to shape the retention course. This amazing result is in the Wosten et al. Paper, which you can analyze this. They have found that soil moisture is related to a first simple coefficient plus some other coefficient multiplied by percentage of clay minus this coefficient multiplied by bulk density minus This is almost impossible to put in an Excel. I have tried and it is extremely difficult. So, this is a very important word, right? Very important word. Right? If you want to use pedal transfer function, you could use this. But for this exercise, we are going to do an exercise now. But we are going to use another model, the rows, which is quite similar but more simple. In this model of pedal transfer functions, you have different metric potentials, different parameters, changing according to this increasing metric potential, and the formula says that the water content depends on one first coefficient plus B multiplied by sand plus C multiplied by by clay, C clay, D and organic carbon, and E and bulk density. How it works is what we are going to do now.